So today we are going to cover 3 use cases. Usually I talk about one use case for 45 minutes, an hour and a half. Today there are 3 distinct use cases, quite short to understand, and trivial solution, but each solution took me about a week to solve. Disclaimer, I love what I do. I may not be the best, so feel free to challenge me. Maybe there's a better solution out there. But this is my approach for now for these use cases. You're always welcome to send me email, contact me, and ask questions. About me, though, for those of you who don't know me, I worked for the last 20 years in startups and enterprises. Started in Java, switched to Scream, opened my consulting company, worked with Walla and investing.com. Black belt in Taekwondo, 3rd degree, skydiving, and I opened this meetup 3 years ago. So a little bit about this community. We have 3 distinct groups called AWS Big Data Demystified, which has its own channel and its own content, which is AWS specific. This meetup we discussed, and BI Analytics Demystified, which has BI-related material, business-oriented, non-technology. Very interesting, started about last year. So this is the lecture. A long time ago, in the past, everything was simple in terms of infrastructure. There was 3-tier architecture. There was a web server, an API, a database, and a data warehouse. Everything was rather simple. Then came the big data, and everything became very challenging and very... Well, basically, the infrastructure exploded every week. Then you know for sure you have a big data problem. Then another problem came, the cloud. And then came the invoice. It became very costly to do a project in the cloud and in big data. An example of stacks for several of my projects, for example, in AWS, in a customer, Walla, 3 years ago, this was the stack. You can see the list of technologies, and this is technologies actually being used in that platform. And in investing.com, this is an example of all the technology stack being used. A bit shorter list, but still very hard to maintain. And it keeps growing. The ecosystem is vast. So basically, I can count about 7-8 different data engineer profiles that can be found based on these technologies. So it's very challenging to keep up in terms of technology. And my solution was to focus on cloud solutions and big data solutions in the cloud and implement data engineering methodologies. So the first use case we're going to talk is the data transfer use case. Google has a DFP service which helps you manage all your impressions on your website, impression of commercial. You can pay Google several $1,000s to get the data, which is impression level based, meaning when a user gets to a website, you just get all the different impressions that was displayed to the user, and if he clicked on it or not, and all the metadata there. The problem is it's highly correlated with your web traffic data, meaning you have 1 billion events like investing, so each page view has about 10 impressions, so you can imagine how much data is sent on an hourly basis. So specifically, I don't know why, but the DFP team decided to send their data in a totally unparsable way, and we had to work very, very hard to parse it, to ingest it. There's no order in the time zones. For example, they send it in your local time zone, but the file name itself consists the time zone of the server side on their end. So, and the actual date value is in a format I didn't find a solution how to parse it with the correct data type. And on top of that, they put several data types in one bucket. That means 4 tables in one bucket without folders. So yeah, somehow needed to separate them, which created a mess because it's one bucket and with a lot of terabytes per hour, and it's a mess. So what was the problem? We had to load everything each day and delete everything each day and do the repartitioning, extract the date, and transform the data. And it made no sense in the beginning. How can we transform it? We couldn't do it on the storage level because the amount of data was too big. Orchestrating it was a bit challenging. And what to do with the date column, we talked about it, but forget that. The cost was $150 per day. So you can imagine the monthly cost. So after a few months of trial and error, we started with the expensive solution just to get the data in the pipeline, started building all the logic on top of that for the BI team. A very long project, many hands took part in that. The idea was to burn money, get to the insights first, determine if it's a meaningful project in terms of data, and then challenge the cost. So after a while, I came up with an idea to switch to a sharding solution. That means instead of loading all the data to one table, I took one shard for file, and then the magic occurred. So just to be clear, everybody know the difference between a sharded table and a partition table? Yes? No? Okay. So a table which is partitioned is one table with many partitions per date. A sharded table is actually a table of tables. There's a table for each day. So when you query the data, you just do select star from T underscore date. Okay, and then you get one partition of one day. So by doing that, I could match one shard to one file, pay nothing for the load because import and export in BigQuery is cheap. And then all I had to do is basic transformation. So the idea was to do that in Airflow. And this was the first time we handled sharded tables in Airflow, and so we had to introduce the concept of dynamic DAGs, which up until that moment we used trivial DAGs. We had to use templated fields. This is a typo, sorry. So it will be easier to make the use case more dynamic. And we had to use the first time loop in the Python level inside the DAG. So I created a blog about this, very detailed, step by step, what I did, what were the challenges. And I want to share with you the actual DAG, so we will see that I put it also in Git, so it will be easier to read. Okay, this is where your DAG begins. This is where your loop begins. I did a loop from start date to end date because eventually we did it incremental. I use one operator that loads data from GCS to BigQuery. And here's what we did in the dynamic operators. We gave a dynamic name to the task ID, so each task will have a date. And for the source object, I gave the prefix and a dynamic name for the suffix that matches the date of currently what I'm trying to load. And the rest is rather trivial. So you can understand that this by itself made the job much simple and solved the ingestions problem relatively trivial, and everything that came after is internal logic, which is not relevant to our use case. To transform the data was easier. All I had to do is just take into account the hour difference on the date manipulation and take it from there. You can do transformation via view or via another job, whatever you wish for. The bottom line in terms of cost, just to emphasize that, it's a 93% cost reduction from $150 daily to $10.5 daily. And we didn't even finish to all the optimizations, we have more. That's about $50,000 a year cost reduction simply because we did something wrong. Okay, questions before I proceed? Okay, next case is SimilarWeb API data pipeline. The use case there was simple. SimilarWeb, for those of you who don't know, give you a competitive analysis of competitor websites compared to your website. For example, investing.com versus Yahoo Finance or Ynet. Okay, you get the amount of page views and visits on your mobile and on your desktop traffic. You can give a simple HTTP request with some dynamic values like start time and the domain you are trying to get. The problem with this use case was that the amount of competitors that I was requested to compare was too big. So the Cartesian product of each API request was about 450 instances per run. So that created about 8,000 requests of API to SimilarWeb. It was the first time we in Airflow needed to handle something so big. The infrastructure was totally unprepared. We used one instance of 4 cores and a low amount of memory. And we wanted to handle that, so we started thinking now. So we decided to use dynamic operators like we did before. And then came a new problem because we had to control the downstream order of execution. Meaning we created 8,000 operators and then some logic about how to proceed if something failed or not. And a trick I realized that I wanted to do some other operations that was correlated to the operator success, but that was a very costly mistake because instead of 8,000 operators followed by say an atomic operator that does something simple like print, and we have now 16,000 operators. So eventually I had to roll back that decision and just switch it down the road after all the 8,000, after I did a conditional that checks if all the 8,000 have finished, whether they succeeded or failed. And another challenge was tuning. I didn't want to deploy a very complex server with thousands of nodes to dozens of nodes to handle it. And we only ran on local executor, which is one instance and a database in the background. So what we did. One, I committed the Airflow configuration over here so you can have a look at it yourself. But the basic gist of it was to increase all the parameters in the Airflow. We can go over it in a second. To increase parallelism, okay? The amount of allowed parallelism on a single instance. The scheduler timeout, which was too short for this use case because apparently a dynamic operator takes a lot of time for the Airflow to be processed. So the scheduler kept timing out on me and I didn't realize what was wrong. And apparently you can add more schedulers. So instead of 2 schedulers, by default I put 8. And that accelerated everything. And I added more juice to the configuration, allowed connections for the SQL in the background. It was bottlenecked to 10 or something. Increased everything without discrimination, added double zeros just to get something running and tune it later. And apparently that did the trick. So the full example of the Airflow is also committed in the blog, detailing all the challenges. Also committed to to my Git. You can see here the loop, the same loop from before, some operators. And then the new thing around here is setting the downstream to set that the API call, the downstream is moving the files afterwards, and then to a wait sequence. Okay. The template was not used here. Anyways, so this is also here. Any questions? Okay, so the bottom line is that using very cheap infrastructure, I ran over 8,000 operators on one machine with 8 cores and 30 gigs of RAM, one Cloud SQL instance with 1 core in 1 RAM. If you had the luxury of waiting, it worked for less than $250. Yes, you can do it faster. Yes, you can optimize it. Yes, you can do a lot of things. But I spent a week on this just to get this job running, and it was good enough for my use case, so it was enough for me. I'm only sharing this because I bet a lot of people tried to tackle this problem and failed because it wasn't easy. Third use case, totally unrelated, BigQML. BigQuery has a cool feature called BigQML, which allows you to do machine learning with several predefined algorithms on your data. Specifically K-means. K-means is an unsupervised algorithm that lets you group your data into several groups using SQL syntax. So basically, the business problem we were trying to solve is based on the web traffic of investing.com, how many groups can we divide the users? Again, detailed blog over here, detailing each step. It starts out like this. You create or replace a model, and you give him the model type, the number of clusters, which is 4 in our, but you can change it to anything you think fits your needs. You give it the data. For our purpose, it was the amount of page views, sessions, and visits. Visits you can ignore for now. It took 1 month. After the model was created, I ran the model on the following month. I limited the results because I didn't want to do in the POC level something expensive. And I started analyzing the results. It was relatively a fast process. There are many ways to analyze it. And the end result was something like this. You got 4 groups with the amount of page views, the amount of sessions, and the amount of visits. Very simple way to save a lot of effort in terms of data science, to do some benchmarking, to test your hypothesis. This is not a production-grade solution. Google does not recommend using BigQML for production. The main use case is to test your hypothesis without a lot of knowledge in data science and machine learning, and then pass it along to your data science team. Let's put it this way. If they cannot optimize the results of BigQML, you're doing something wrong. They are doing something wrong. So the main use case here is benchmarking. I wanted to share with you because it took me about 3 hours to answer a question without prior knowledge on K-means. Summary, just to wrap everything around, my motto in this meetup that a good architecture in big data is it fast, is it cheap, and is it simple to maintain? This is how I think when I designed a new solution for a use case. Call for action, I would be very happy if you join the meetup. RSVP, like, subscribe to our YouTube channels. That will help my community, our community grow. You have all these links with all the information, the meetups, the YouTube channels in plural, the website, my phone number if you have any questions. I'm usually a nice guy. I smile a lot. I love to help a lot. So feel free to contact me if you have any questions. And that's about it, unless you have any questions. Miles? No questions? OK. Thank you very much.